almost 1/3 of the mangroves worldwide has been depleted. And for that, if we want to protect them or better or sustainably manage them, we need to first identify or regularly update the mangrove extents and their health over time. So what I'll trying to show you today, some of the techniques that we use in remote sensing, basically using satellite images, and then I'll show you how that can be used in India as well. So we do have some global data sets. So if you go to this website, which is hosted by the center where I work. So I work at the Center for International Earth Science Information Network, CESIN in short. We are a center under Columbia University's Earth Institute, and we also host a NASA data center. So being a NASA data center, we collect data sets. Some of them are developed by us, scientists at CESIN. Some of them are third-party data set. So I would like to reach out to you, and if you know any remote sensing derived satellite data products that you'd love to spread across everyone, all across the world, please do contact me. We have many different data products, not just Mangrove, but the one that I would like to show you today briefly is the one that was developed by Dr. Chandragiri and his team. It's a global mangrove data product based on 2,000 satellite images. They are also working on updating that data set for 2015. So hopefully that will be available through CDAC in a year or two. Now the question is, if we already have global data sets, why we need more data sets, right? You can just use those and focus on your study area and use that. Well, one thing is, we need regular updates. Landscapes are changing very fast. If you are working with a small area that's going through a lot of changes, you probably need an annual data product, which is very challenging to create for a global data product. So if you are focusing on a single country or even a region, like you're focusing on Mumbai or Indian Sundarbans, you need a regular data product. So you cannot really use the global data set. If you are interested in just 2,000, then yes, please feel free to download the data set, which is free, use that. But if not, then you have to create your own data set. Now, some of the global data sets, they often compromise with the accuracy at local scale. And it's easily understandable because if you're working at a global scale, it's very, very challenging to sustain that a very high level of accuracy at each and every corner of the world, right? So at some places, it will be very highly accurate. Some places, it's not. So if you are lucky, you'll work on an area which has very high accuracy. You are not, then you are out of luck. Also, if you are focusing on a single country or a landscape, it's easier these days with the advent of new technologies to create these data sets. Previously, when I started my career 10, 12 years ago, it would take me months to create a single data set. These days, it takes only weeks. You have to have that kind of skills, however, but it's possible to create those estimates. So the one project that I would like to discuss today is a USAID project. It's called WABIC. The full form is West Africa Biodiversity and Climate Change. So basically what we are doing here, it's the goal of the project is improving conservation and climate resilient low emission growth across West Africa, which I think many of you could relate to. Now this is a huge project and it's led by a company named Tetra Tech, and we are one of the many partners. So we are partnering with government agencies across different countries in West Africa. We are working with NGOs. We are working with agencies or research institutions in West Africa and also in other parts of the world who have expertise in these regions, basically focusing on three core components. Component one is combating wildlife trafficking because it's a huge deal in West African countries. Number two is increasing coastal resilience to climate change. And number three is decreasing deforestation, forest degradation, and biodiversity loss. So I am leading part of this component two, which is increasing coastal resilience to climate change. So for that, I just finished the mangrove mapping for Sierra Leone. We will move on to other countries soon, but for now, I'll just show you the results from Sierra Leone study. So Sierra Leone is one of the West African countries that's under this WABIC project. The size of Sierra Leone is about 72,000 square kilometer, which is slightly smaller than our state of Jharkhand. It hosts about 6 million people. Many of them are along this coast. So our team, field team, they recently completed a vulnerability assessment for these areas. So these photos are from the field. They were taken by my colleague at Season, Dr. Sylvia Shoshka. And what you see here on top left is a photo of a village. I don't know if you can see, there's a hut in here. And there are many villages along the coastlines, the one that I showed you. As you can see here, that's a rice paddy. That's a rice field here. So this is right along the coast, right along the river. There are many rivers there. It's right along the rivers, and you can also see the soil erosion here. This is a typical scenario there. On top right, you see a rice paddy. This is about 4 kilometers from the coastline. Here you do not see the mangroves. The villagers told us, the team, that there are still mangroves along the coastlines because these people, they prefer to do farming. They are far away from the coastline. They do not need to cut down the mangroves. So there are still mangroves. So in some areas, you would see mangroves near the coastlines, and some areas you would see they are completely being depleted. What you see here is it's giving you an example what these people do with these mangroves. They cut down for their sticks, some use in construction, but mostly is being used for fish smoking. So there's the fishing communities. They prefer mangroves because it burns for a long time. It gives more smoke than fire. So it takes the fish that's being smoked, it gets a nice flavor. So that's why they prefer mangroves over other woods that's available. Here you see a site that shows regeneration probability. So I'll show you in some areas mangroves are being heavily depleted, but are they coming back? Some areas yes, some areas no. This is one example where mangroves are coming back, and as you can see, as you will see when I show you the results, you can see fluctuations in mangroves coverage, meaning there have been mangroves and then people are cutting them down, and after a certain time they are being left out and mangroves are coming back. So you can distinctly see the coverages like going out and coming back. What you see on top left is a village in high tide. It's close to the coastline, and as you can see, they're completely flooded. Think about the scenario where there's a surge, like a storm surge, and sea level rising. So this village will be completely wiped out. Here's another village on top right. It's in low tide. As you can see, there's no barrier at all between them and the coastline. So they're really very vulnerable, and they have no idea what's going on because in their mind, mangrove is one of the inexhaustible resources. So they do not understand that if they cut down mangroves, it might not come back. In their mind, it's always coming back and they will be protected. And some people don't even understand that mangroves are actually a good protective barrier between them and the storm surges. What you see here is just to give you an idea of the scale of this fishing community or the fishing activities. All these little boxes or whatever you call them, they are full of smoked fish. So they use the mangroves. They do this about, I think, 54% people in all those villages that were visited during this field visit last summer, they use mangroves for this kind of activities. What you see here is show that there's also a public health component to this problem, because most women spend major chunk of their time in the kitchen with this smoke because they need this smoke, right, for the fish smoking activities. Children, especially girl child, they spend a lot of time with their moms inside the kitchen, and they are inhaling that smoke. So there's obviously a public health component to this problem, not just environmental problem. So here what you see, I'm not sure if you can see the two colors. We started with That's fine. I mean, we will need that in the next moment. So what you'll see here, the lighter green color here is the GIRI data that I just mentioned, the global 2000 data set. Because when we started this project, we did not have any other data set available to us, so we did not know where to begin with. We wanted to have a baseline carbon stock because the project is starting in 2016. So we wanted to create a 2016 data set, but we also wanted to do the vulnerability assessment, and for that we needed to know where to go out in the field. We only had this 2000 data set, and we also had a 2014 USGS data set that was available to us through collaboration. It was developed by Gray Tapan at USGS. So we basically overlaid these two data sets. So if you see the lighter green color, maybe here and there, that means it was mangrove in 2000, but it was not mangrove in 2014. That's why you can see this 2000 data, because if there's a 2014 data, it will cover the 2000 data, right? So we started from there. We chose 4 focus areas for West Africa, for coastal Sierra Leone, all along the rivers. This is the top left, the left panel is from northern part of coastal Sierra Leone here, and the right panel is from southern part of coastal Sierra Leone. In northern part, we have Scarces area and SLRE, which is Sierra Leone River Estuary, and in southern coastal Sierra Leone, we have Yori Bay and Shebro. Now all these red dots denote location of a village. The bigger the dots are, the more population there is. So you can see there's quite a bit of population. They're right across the coastlines. So as you can see, they're really very vulnerable. Now when we know that, after we did this kind of comparison, we knew where to go for the field work. But we cannot really use this to understand how mangroves have been changing over time. The reason is you cannot really compare apples and oranges. So these two maps were created using 2 different methods. And as with any method, there are certain uncertainties that come with a data product. If you are incorporating 2 different data sets for your analysis, that means you are bringing in 2 different types of errors. And oftentimes, it's very difficult to quantify that type of error because it's coming from 2 different sources. So for a project like WABIC, we were interested in looking at landscape evolution over time, and it's very important to keep the method consistent. So once we had this idea, I went ahead and created this map for Sierra Leone for 2016. So in this map, you can see 4 different land covers. The blue ones is water and wetland, green is mangrove, light green or kind of yellow is other vegetation like farmland, grass, shrub, and this orange one is bare soil or built environment. For coastal zone, I focused on elevation lower than 40 meter, which is a cutoff value that is widely used for low elevation coastal zone. I used 3 different satellite data. For elevation, I used the SRTM data. For classification of the images, I used Landsat 8, and for validation, I used Sentinel-2. So for validation purposes, just for this kind of mapping, these days, you do not have to go out in the field. 10 years ago, you probably have to go out in the field and collect data yourself using a handheld GPS. These days, with the advent of new technologies, we can do that from your office desk. The accuracy of this map is about 96%, which is pretty high because generally these data sets come with about an 80% of accuracy. You have probably seen this type of map of different things, just not mangrove, forest or cropland. What I wanted to show you today or tell you is the story behind these maps. How satellites see things, how do I create this kind of map from satellite data? So for that, we need to go back to the basics, the electromagnetic spectrum. So as you know, any energy, any type of energy can be expressed in wavelength or frequency. So in the top panel, you see the wavelength. Towards your left, there is a longer wavelength. If you move to your right, these are shorter wavelengths. Corresponding to that, here is frequency. So the longer wavelengths, they have lower frequency, so they are big waves of energy, and the shorter wavelengths, they have higher frequency. So here we are focusing on a part of that electromagnetic spectrum. This is what we use in remote sensing. We do not use the entire spectrum. We just focus on a part of the spectrum here. So this is a close-up of what we see. So we basically see the VIBGYOR, right, the violet to red, and a combination of these colors. Luckily for us, satellites see more than that. They can see ultraviolet, they can see near infrared, sometimes they see thermal infrared. So definitely they are more capable to see things. So how do they see things? So satellites basically, they come in two different flavors. One is passive and the other one is active. This is passive optical remote sensing. As you can understand from the name, they are actually not doing anything actively, meaning when sunlight hits a surface, like a target, maybe the rooftop or maybe a tree canopy, some of that energy is being absorbed by this target and some are being reflected. These passive satellites, they capture that reflected portion of the spectrum. So for example, if sunlight is hitting a surface, 70% may be absorbed and 30% is being reflected. Now the reflected portion of the satellite, the sunlight is capturing and breaking them in different channels. So some will be captured, say, in band 1, some will be captured in band 2, depending on what are those channels that's set in the sensor. Different satellites see in different bands. Like we can see different colors, different satellites see different bands. Depending on how advanced they are, they have like more bands. So for example, our hyperspectral sensors will have hundreds of bands. The ones that I use for my work, they have something around 7 to 11 bands. Now the problem with passive remote sensing is something, this fluffy white stuff, the cloud. Since this is passive remote sensing, they cannot penetrate the clouds. Now if you are working in a country, a tropical country, it's a very common issue. Especially if you remember from the video, it showed that most of the mangroves are from 30° north to 30° south. So a lot of them, probably all of them, are tropical countries. Now if it's focusing, you are focusing on Indonesia, Malaysia, it's always raining probably. So most of the time we have this in our image. So this is a satellite image, and since we have clouds, we cannot really see through them. So we do not know if there are mangroves beneath that cloud. And sometimes I have seen images and you don't want to see them, trust me. It's completely covered by clouds. So what's important then is the return time of that satellite. Return time means how often a satellite goes over or flies over a particular point. So if this is the place that I work, I would want, in order to avoid this cloud issue, I would want the satellite fly over my head as frequently as possible. Because if it flies over once a month and say 6 months are clouded, then I really don't have any data to work with. So the frequent the satellite flies over this particular space, the better chance I have as a remote sensing scientist to have good data to analyze. So return time is very important. But is there any other way to deal with that? Luckily, yes. So here we are talking about active remote sensing. For active remote sensing, we have SAR, which is synthetic aperture radar, and also have LiDAR. So here the satellites emit signals and it bounces back through the surface, and the satellite then captures it. So basically you can take pictures of Earth's surface. It's literally taking pictures nighttime, because we do not really need sunlight. You can also do it through rainy season. Now the problem with active remote sensing is it's completely new, like not completely, it's comparatively new, like when you are comparing it with the optical remote sensing, the passive remote sensing. And it's, the coverage, it's kind of spotty. Sometimes you have it, sometimes you don't. So if you are interested in a historical land cover mapping, you want to know what was there back in 70s, you are pretty much stuck with the passive remote sensing. That's what I have been using for my work, because for that project, the WABIC project, we wanted to know how things have changed over the past 27 years. So this is kind of to give you an idea how satellites see things. So as I mentioned, we see things from violet to red and a combination of them. This would be something comparable for satellites. They see things in band 1, which is lower than blue, which we can see. They also see here shortwave infrared, which obviously we do not see. So the way it works that, say for example, if I'm seeing something blue, that means that particular object is reflecting blue light. That's why I'm seeing it. So if an object is reflecting shortwave infrared, we won't be able to see it, but the satellites would do that. So whenever we are working with satellite images, we need to think about 3 different things, 3 resolutions. One is the spectral resolution, basically meaning how many bands it has. So the more bands it has, the better is the spectral resolution. Next is temporal resolution, the return time. If it's coming back every 16 days, it's kind of a good balance. I mean, there are satellites that come back every day, like MODIS. We have daily data. Then we have spatial resolution, meaning how fine the data is. So think about it. We all have taken pictures. Have you ever tried zooming in on the picture? If you zoom in and keep zooming in, at one point the picture will be broken. When we say that the picture quality is not good, you basically see the small squares, which is the least mapping unit. It's called a pixel, right? A common word for all your camera phones. Pixel is the building block of any image, be it taken by satellites or your camera phone. Now for a Landsat, the pixel size is 30 meter by 30 meter, a 900 square meter. There are satellites which are sub-meter, meaning the pixel size is less than 1 meter, like one side. And there are satellites for which the pixel size is 1 kilometer by 1 kilometer. So depending on what you are interested in, the application, the problem, you choose your satellite. I personally like Landsat because most of my work has been at a regional level. So Landsat is kind of gives me a perfect balance for everything. Because if we want to go high resolution, for example, if I want to map each and every car parked in a parking spot, I obviously can do that using high resolution imagery, but then the area covered by that would be pretty small. Because the high resolution you go, the smaller the footprint gets. For Landsat, one Landsat scene covers around 180 kilometer, 170 kilometer by 180 kilometer. So it covers a nice range. I mean, you might have to stitch a few depending on where your study area is, and if you are lucky like me, for my PhD dissertation, my location, my study area was right at the intersection of 4 Landsat images, although it could have been covered by just one image. So it depends, because there's a path of the satellite to fly through, right? So when it passes through a place, depending on where your location is, you might need to use multiple images, but that's a pretty nice size, I would say. So Landsat is kind of a perfect balance if you are going for a process that's not going through a changes which is less than 30 meter. So 900 square meter pixel is good enough for you, and also the temporal resolution works for you. So what you are seeing here is a spectral reflectance curve, which is basically how different surfaces reflect sunlight. So this one is for soil, the red one, the green one is for vegetation, and the blue one is for water. As you can see, they're very distinct. So satellites can actually mark the differences and send back to me some data that I can work with. So what do I do with those images? Once I have that image, each pixel giving me certain value in different bands, I can either do manual interpretation, which is very time consuming and it's not possible to do. Automated, it's getting much and much, like more and more easier these days. I do that, And then you can do different types of analysis. What I'll show you today is for the unsupervised classification technique. As you can understand from the name, it doesn't need any supervision, and that's the beauty of it, because I don't have any information back from the 70s or back from the 80s. So I need the computer do it purely on empirical basis. I do not want any subjectivity into it, right? So as I mentioned, depending on the values, the digital numbers, I'll ask the computer to divide them into different beans. Think like I'm giving you a bowl full of candies of different colors. So if I ask you to put them into different beans, you will probably decide to put all the reds together, all the greens together, all the yellows together. So you are doing it on the basis of color. If I'm giving you all the candies, same color, but of different size, then you will probably do it based on the size. So the computer, the machine, it's a machine learning technique, so it will do it based on the spectral signature value. Then, as a remote sensing scientist, my job is to use my experience and expertise to label those. So based on either field data or my experience of knowing different spectral signature, I will say, okay, this cluster is probably water. So if cluster 3 and cluster 6, they look same, I think this would go to say conifer forest. Or if cluster 1 and cluster 4 look same, they will probably be classified, they should be classified as water. So I label them. And then once they are all labeled, you merge the same classes. So from this image in your left, you end up with a map like this. And this is what you saw on the first, the 2016 map. But I didn't just have 2016 map, I also have a 2010, a 2000, and a 1990 map. Luckily, these days you can do all of these on the cloud geospatial platform, which is Google Earth Engine. I use this because you can access all the data sets that needed for this kind of analysis for free. Well, it was free, but before you have to download them separately, pre-process them, put them together, do all your analysis. It will take you months. These days, it has become so easy that you can do everything on your laptop. You do not even need a high-performing platform, laptop, because you can do everything on Google's platform. You just call it. You have to write codes, but it's pretty easy, and there are some tutorials that you can access to. So, and it comes with metadata. So you can go ahead, and it's very interactive. It's not like if you do not like to write codes, you will probably like this because it's very interactive. It tells you where you are going wrong, unlike other computer languages that just gives you red errors, like red flags. So you can use this to do all your analysis, and it's pretty fast. So what you see here, can you just dim the light for a moment, please? So this is the northern Sierra Leone, and this is the southern Sierra Leone. The light ones, the light color is for 2010, and the darker one is for 2016. So I'm not sure if you can see it here. This is where you see the lighter ones, not everywhere. It's just in the Scarces River estuary. A lot of lighter ones, meaning a lot of mangroves were cut down or depleted, degraded after 2010, between 2010 and 2016. Now, if you want to know the exact time, you have to do an annual update. It was not needed for this project need, but it's possible to do it. But so we knew that after 2010, it was depleted. This was between 2000 and 2010. And as you can see, you do not really see any light color, meaning it was either stable or it was regenerated. If you want to know whether it was regenerated or not, you have to put 2000 on top of 2010. I put 2010 on top of 2000, so that's why you just see the darker color. But it's possible. So this is just visual, comparison. If you go back to 1990, you again see a lot of light color here. So as you can see, there's a fluctuation. You see a lot of deforestation or depletion going on between 1990 and 2000. Nothing happened for about 10 years. Then again, there's a chopping down going on, especially in this area. And our field team, they actually confirmed this finding because they saw, as I mentioned, some regeneration going on. So obviously, trees were cutting down there, and when they talk to people, they also mentioned that a lot of people actually do that, and which was interesting that they found a lot of people from other parts of the coastal communities, like other coastal communities, they go up there and they cut down trees. So they don't do it in their nearby communities. They go out to other portion of the country and then do it. And it's pretty close, it's not that far, so they can do it. Now, for the policymakers, if you want to show them the maps, it's pretty self-explanatory, but sometimes they prefer numbers. So you can put together all of this, and you don't even have to say anything because it's self-explanatory. So the leftmost column is for the Sierra Leone estuary, the rightmost column for Uri Bay, and in each graph you see 1990 to 2016, how these different land covers are changing. And as you can see, just take Shebro, it hosts most of the mangroves that's there for coastal Sierra Leone. So if they want to protect it, they should go to Shebro. If you can see Sierra Leone River estuary, other vegetation is the dominant land cover. So if WABIC professionals on the ground, they want to focus on replanting, they should probably go to this area. And there are different things that you can interpret from or extract from this graph, which is basically a quantification of the satellite techniques that I just showed you, remote sensing techniques. And I also did it at different distances from the coastal line. So the top row is from 1 kilometer, this one from 2.5 kilometer, and the bottom panel is for 5 kilometer. They are not mutually exclusive, so the larger buffer, they encompass the smaller one. This is just because of the finding that I showed you that the coastal communities that are farther away from the coastline, they claim that they do not extract mangroves because they don't want to go to the coastline, like 4 kilometers from there. They would rather do it closer to their home and do the rice farming. Now, with that, we can also do a carbon stock assessment because this is the in thing right now, right? Putting a price on carbon. So how do you do that? Well, one thing, the most accurate way to do it is go down out in the field, take measurements, very detailed ecological measurements, come up with the allometric equation, then study the heights of the mangroves, and then convert to biomass. But it takes a lot of time and a lot of money. Plus, if you're working in a heterogeneous landscape, you cannot really measure each and every square foot of that area. And you cannot extrapolate. You cannot really use a measurement that you took here to some place from 4 kilometers from here. So what we needed is just an estimate, just to start with something, because this is really the first ever study in Sierra Leone that's giving us a historical view, how mangroves have been changing over time and space. So we just needed some numbers, some estimated numbers, not the most accurate numbers. So what I did here, I used numbers from literature. So there have been published studies that have done some detailed methods, detailed ecological data gathering, and they came up with some numbers, carbon stock numbers, in metric tons per hectare. So I calculated the area from my maps, and then I multiplied that with this number to come up with the mangrove carbon stock. It's in megaton. So as you can see, again, since we have a lot of mangroves in Shebro region, we have a ton of mangrove, a megaton carbon here. So if we want to store that carbon and keep it stored, we'd probably focus on here for protecting that mangrove, and in other areas for sustainably manage. So as you can see, depending on how much mangrove we have or what type of mangrove we have, the type of activities change. Somewhere it's protection, and somewhere it's sustainable management. Now, can we use those techniques for India? The beauty of remote sensing is that the data is uniformly available all across the globe, so you can use the same techniques, same data set, same methods for India as well. But what I showed you is only one thing that we can do through remote sensing. We can do many other things, and of course it will take me like maybe 1 month at least to describe everything. So I just wanted to show you one more thing that we can do using remote sensing, is how we can look at vegetation health. So for that, I would like you to revisit the spectral reflectance curve, and I would like you to focus on this vegetation curve just for these 4 bands. What you see here, there is 2 jumps here. One is here, this is the green band, and that's why we see trees green, because they absorb blue and red, healthy vegetation, and they reflect green and near infrared. Now, if we were satellites, the color of healthy vegetation for us would be near infrared. Now, we cannot see near infrared. That's why the healthy vegetation is green to us. Now, for satellites, healthy vegetation is near infrared. And as you can see, there's a huge difference in that. So this is what we call a vegetation edge. Basically, we tweak this information or this behavior of vegetation to understand how healthy vegetations are. So for example, you might have a mangrove here, like a mangrove patch of mangrove forest, but it might not be healthy, or it might be sparsely distributed if you compare it with 10 years ago. So what we do, we can use different indices, we can create different indices using that behavior. Now that behavior is based on chlorophyll and the internal structure of leaves. Different species, they have different internal structures. They reflect differently. And based on that index, we can identify different indices. It's a crude measure, but it can still work. So this is for Sundarbans. And this is from last 4 months, from 2017. This is showing an index, a very commonly used, widely available, very easily computed index, which is called Normalized Difference Vegetation Index, or NDVI in short. If you are into remote sensing, if you have taken any class in remote sensing, you'd learn about this NDVI, no matter what you learned, what else you have learned, or you have not learned anything. This is the single most vegetation index that was probably like very old and has been consistently being used for different applications. This is basically a ratio of near infrared and red. So it's NIR minus red divided by NIR plus red. It's basically highlighting the vegetative behavior of NIR reflectance. So NDVI ranges between -1 to +1. To show you the differences, I'm just showing you the range from -0.3 to +0.5. Red means low value in NDVI, meaning either it's not vegetation or very dry, non-healthy vegetation. Mostly it's for salt pans or water or soil. Then dark green means healthy vegetation, and something white or light greens means something in the middle. So this is for 2017. This is from 2000. So suddenly you see a lot more dark shades of green. Now, does that mean that 2000 we had like healthier vegetation? You can do it like a visual comparison, and I'm focusing here just on this island, particular island. It's called Jharkhali. It's one of the many islands in Indian Sundarbans, and I'm focusing because this was my study area for my master's thesis, nothing else. But as you can see, a lot more white and red here in 2000. In 2017, more green. But does that mean it's more mangrove? First of all, let's quantify. Let's not trust our visualization capability, and let's just go on with the empirical analysis. This is called an NDVI differenced image. Basically, you subtract one image from the other. So anything green means 2017, the later date, had healthier vegetation. Anything white or red means 2017 have seen a deterioration in vegetation health. And as you can see, most of this image is different shades of red, which confirms that over time it has deteriorated, even though it was bright green in one image. So I'm just trying to convey this message that do not trust just with one timestamp. If you want to understand how things are changing, how mangroves are changing, do not just go with the extent. look at how they are changing, where they are changing, look at different indices. This is just one index. There are many other different indices. Depending on your application, you can choose different indices and go ahead with the quantitative analysis, and you will understand how things are changing. Now, what you will see here is a little green patch here in the Jharkhali Island, but does that mean it's better mangrove in 2017? Probably not, because these are all croplands. So you are interested in mangroves. What you would do? You would create a mangrove map like the one I explained before, the one in West Africa. You will probably create a mangrove mask and then just focus on those areas to understand how mangroves' health is changing. So that's how you can combine discrete pixel-based analysis with this continuous index-based analysis to come up with something meaningful, and that's something you can convey to people, the policymakers, to local stakeholders, to conservationists. There are many different techniques. As I mentioned, it will take me months to explain everything, but my recent interest has been in microwave remote sensing, which gives you more flexibility in terms of understanding structure of the mangrove, and also this is active, so no cloud issues. So maybe next time when I'm here, I'd like to show you something from that. So with that, I'd like to take any questions you might have.